This project is about an interactive system for helping users simultaneously rank a set of nuanced or subjective choices and also find an explanation for that ranking, which we'll do by ranking candidates for a fictional award given for being the best cat. This is our explainable ranking interface. On the main page, we start out with all of our choices in a docking bin on the top left here, and a visualization of our criteria weights at the bottom right. Our current ranking will go on the bottom left here, but we'll have to populate it first, which we can do by dragging items around or by setting the current ranking to some linear combination of existing criteria. So to get us started, let's rank all of our cats by the provided fluffiness criteria. If we go up to the top of our ranking, we'll see that Guinness has taken the #1 spot, and if we scroll down, we find Pickles shivering away at the bottom. And that pretty much makes sense. So now let's take a look at what this coolness criteria means. If we sort by coolness, we see Hansel and Samantha at the top, and I think we can all agree that they seem pretty cool. And if we go to the bottom, we see poor Pickles again, which we may not agree with this judgment, but we can at least understand where it comes from. But we're a little more concerned to see Amy so far down the list, because she clearly has some technical skills. And if we look at her bio, we find that she has a bachelor's degree in information science and can type 80 words per minute. So this coolness metric has clearly failed to capture something, and we'd like to see if this is happening to any other cats as well. So for this, we'll go ahead and create a new criteria, which we'll call skills, and describe as has useful skills. And if it's ethically appropriate in this particular application, then we have the option of using AI to try and find items that match this description. So we'll go ahead and do that now, indicating that the LLM should look for matches in the strengths section of each cat's bio. And now we see our criteria panel, where we'll sort items from a neutral bin on the left into positive and negative groups of different values on the right. And since we asked our AI a binary question, the neutral items will be color-coded blue if it thinks the answer was yes. Looking through its results, we see that it correctly identified Amy, as well as Figaro, who can drive stick shift and has a good credit score. Then Jellybean is a real high achiever with degrees in communications and law, as well as a large Instagram following, and Houdini, who has some stage performance skills. So let's give Jellybean a +3 for her post-bachelorate degree, Amy will get a 2, and the other two will get a 1. And since the rest of the cats are mostly into napping and purring, we'll leave their scores neutral. Now, if we think these criteria should be enough to explain our own subjective ranking, then we can try to guess that explanation in the form of relative weights for each criteria. And to help us visualize this, we can also switch to the score distribution panel to view how scores are distributed across choices and criteria for the current explanation. And we can optionally use these weights to update our ranking. But to see how well we did, we really need to check this using pairwise comparisons. For this, we'll use one application of what we call the user insertion sort in our paper, where we take this estimated ranking and use it to accelerate a process that results in a verified ranking based on head-to-head comparisons. And our system will automatically serve the right pairwise comparisons to the user, adapting to each response until it converges on a final order. Now our ranking comparison panel shows the difference between this final ordering above and the one that our proposed explanation predicted on the bottom. And we can see that they don't quite match up. So now we could try to search for a different explanation by adjusting weights, but this amounts to a manual high-dimensional search, which is pretty hard. So instead, we'll use an SVM to try and optimize for weights that explain our ranking, and see that, in this case, our ranking is actually impossible to explain using the current criteria, which means something must be missing. So let's go ahead and add a new criteria, which we'll call something missing for now. And this time, our system will try to guess the value of this missing criteria based on inconsistencies with our current target ranking. And now, if we look at the cats with low predicted scores, we see that they tend to just have bad pictures. So we'll make this new criteria a measure of how photogenic each cat is. And after a bit of sorting, we'll add it as part of our explanation. And now if we use our SVM to infer weights again, we have finally found an explanation for our ranking. But this doesn't necessarily mean that we're done, because this explanation tells us something about how we valued items in our ranking. And we might decide, for example, that we don't want this ranking to be about how photogenic or how fluffy each cat is. So this explanation gives us an opportunity to introspect and think about how we value things. which is also reflected strongly in our user studies. These are just some of the features in our system, so for more information, please see our paper. Thank you.